Hi everyone, welcome to session number 8 for the concentration inequalities course. So in this session we are going to discuss assignment number 7. So let's begin. Let x be a real valued random variable with standard normal distribution. Which of the following are true? Jx and x denote the Fisher information and the entropy power of the density of x. Okay, so let me recall what Fisher information is. So Fisher information would be, so suppose uh, q is the density, so q is the density function of this normal 0 1 random variable. Okay, so jx, this is basically expected value where x is coming from n0 1 ln qx the whole square, right? So which, if we just write what this expectation is, it would just be dou ln qx the whole square times qx dx. Okay, where the integration is from minus infinity to infinity. So now for the normal distribution, we know that the density function q is 1 by square root 2 pi e power minus x square by 2, right? So if you just take, so what would be ln of qx? It would be ln of 1 by root 2 pi plus ln of this e power thing, which will just give us minus x square by 2. Okay, so and once we take derivative, this ln of 1 by root 2 pi factor will go away, and we'll only have this x square by 2 factor, the square of that. So what this becomes is x square by 4, right? The q of x dx. So this is just expected value of x square by 4, right? Um, where x is a normal random variable. Okay, so what does this give us? So I'm sorry, this would be x power 4 by 4. So this is the expectation of x power 4 by 4. Okay, and now what is the fourth moment of a Gaussian random variable? So um, fourth moment of Gaussian random variable would be, I think it's 1 by 4 into expected value of x by 4, right? Which would be what? I think it's 3. So 3 by 4, which doesn't match any of these answers here. Jx is d of ln qx the whole square. Oh, okay, I forgot to take the derivative here. So let me do it again. So what will happen is, okay, we'll remove all this. Okay, so okay, so you have to take the derivative of this minus x square by 2 with respect to x. So what that will give us is just x. So this would be this would just be expected value of, okay, so the derivative of this uh, derivative is x, and then you square it, right? So we have expectation of x square, which is 1. Okay, so jx is 1. Now let's calculate nx. So nx is expected value of minus ln q of x, right? So now again we know that what would this be? So ln q of x, just like before, it's like ln 1 by root 2 pi minus x square by 2, right? So this would be, okay, so it would be just ln of root 2 pi plus expected value of x square by 2, okay, which would be half ln 2 pi plus 1 by 2. Okay, so actually this is not n of x, this is h of x, this is the entropy, and then entropy power is e power 2hx by 2 pi, right? So yeah, so this would just be, if we just raise everything to this power, so we'll have e power, so this ln thing will come down, so it will just be, okay, let's write it down. So it will be 1 by 2 pi e ln 2 pi plus 1. Okay, so this would be e power log of 1 by e um, plus 1 by 2 pi e. Okay, actually this formula is wrong, it's just, okay, it's e power 2 hx, the whole thing 2 pi, right? So now if you just substitute here, it would be e power ln 2 pi into e by 2 pi e, which is 2 pi e by 2 pi e, which is 1. Okay, we got there finally. So hx jx is 1 and nx is also 1, right? And we had this inequality, Stamps inequality, which says that jx into nx is greater than equal to 1 for every random variable x with a density. So Gaussian random variable achieves the equality here. Okay, both jx and nx are 1, and so jx into nx is 1. Okay, question number 2. Let x be a real value random variable with finite variance. Let q be the density. Let nx denote its entropy power. Let y be ax plus b for some constant. Which of the following are true? Okay, so q is the density of x. So let's see what the density of y would be. Okay, um, so okay, so let density of y be h of y. Okay, so we want to compute h of y in terms of q. Okay, so let's see. Okay, so what is this probability that y is less than equal to y? This is a CDF of y, right? Which this would be same as probability that ax plus b is less than equal to y, which is same as probability that x is less than equal to y minus b by a. Okay, which is the CDF of x at y minus b by a. And so now take derivative on both the sides. So derivative of this, so derivative, right? This is h of y by definition, because we assume the density of y be h of y. And the right hand side, again take derivative Okay, so this would be 1 by a. You're taking derivative with respect to y. So 1 by a q of y minus b by a. Okay, so now let's see what n of y would be. So first we'll compute h of y, the entropy, differential entropy. So okay, two h's here. So let's see. H of y is defined as small h of y is log of 1 by h of y dy. All right, so now we'll just substitute what h of y is. So okay, this would be 1 by a q of y minus b by a ln 1 by a q of y minus b by a dy. Okay, so now let's do change of variable. So let t be y minus b by a, right? So which means dy would be a times dt. Okay, so which means this integral would be equal to q of t ln 1 by, so ln a q of t dt. All right, which would be, this would be ln a plus q of t ln 1 by qt dt. Right, I mean this was q of t ln a dt, so ln a would come outside and q of t dt would integrate to 1, right? So this is just ln of a, and this is just what this is, h of x, right? So now we want to compute entropy power. So n of y is e power 2 h of x by 2 pi e, right? So what we'll have is e power 2 ln a times e power 2 hx by 2 pi e. Okay, so 2 ln a is ln a square and e power that, so through just a square, and then this part, it's just n of x. So it's n of x. Alright, so n of y is a square n of x. So B is the correct answer. Okay. Right, so let's see if it makes sense. So suppose a is 2 and b is 0, right? So what will happen is, so then if density of x suppose looks like this is q of x, right? So the density of y, so y would be, y is 2x here, right? So the density of y would be broader, and so density of y would be something like this, right? This would be h of y, right? Or h of x, right? So its density is wider, so what that means is that the entropy is higher because there is more uncertainty. The more uniform something becomes, the more is their entropy. So n of y would be like this says it would be 4 times n of x, right? So it makes sense. I mean, it makes sense that the entropy is more than n of x when a is more than 1. When a is less than 1, the opposite happens. The density of h shrinks, and so the entropy reduces, right? So that is why D is not always correct. D is only correct if a is more than 1. Question number 3, let x be a real valued random variable, finite variance, q. Okay, the same setup as before, except that we now want to compute j. J is, what was j? Fisher information, right? Okay, it's here, Fisher information. So h of y, h of this y, okay, small h of y, it's the density of y. Let, okay, and we saw that h of y is 1 by a q of y minus b by a. Okay, and now what is j of y? J of y would be dou ln h of y the whole square times h of y dy. Okay, this is just a formula, and where this derivative is with respect to y, right? So now let's just substitute. So it's dou 1 by, so it's ln 1 by a q of y minus b by a the whole square times 1 by a q of y minus b by a times dy, right? So now we just have to remember that this derivative is with respect to y, right? And here we have y minus b by a, right? So what will happen is, so again you can break this as ln 1 by a plus ln q of y minus b by a, and when you take the derivative of ln 1 by a, it would be 0. Okay, so we just have to worry about this ln q y minus b by a, and okay, and so once you take derivative of this, uh, there will be this 1 by a factor which comes out because of this division by a, and then there is a square here. So finally what we would have is 1 by a square right, b 1 by a square, and then yeah, the normal log, so the normal thing, so would be, okay, so what would this be? But if you take derivative here, this would be q dash of y minus b by a times 1 by a upon q of y minus b by a, right? So this would become q dash of y minus b by a by q of y minus b by a the whole square times 1 by a q of y minus b by a times dy. Okay, again make change of variables, so let t be y minus b by a, so then this becomes 1 by a square q dash of t by q of t the whole square times q of t dt, right? And this is just dou ln q of t, with derivative with respect to t the whole square, right? So this is overall just 1 by a square j of x, right? So C is the correct answer. Okay, and so again, if we just see, if let's say y is 2 of x, so if this is the density of x, right, so the density of y would be a broader density. Okay, so when the density is broader, okay, so there are two notions of information for a random variable, right? What we are saying here, one is the entropy, which measures uncertainty. The more uniform something becomes, the higher the entropy. And on the other hand, we have Fisher information, which is the opposite, which means if if it becomes flatter, the Fisher information decreases. So it's basically because of this derivative of h of y, right? So uh, and so 1 by a square would be 1 by 4. So this says that Fisher information decreases by 1 by 4. Okay. And so again, if you see Sturm's inequality, it's like j of x times n of x is greater than equal to 1. So what this is saying is that their product is greater than equal to 1. So if nx is small, if small. Okay, what does this mean? This means that entropy is small, which means the density is concentrated, right? It's not very spread out. So, which means the Fisher information is large. Okay, the more the curvature, the more the Fisher information. So if this thing is concentrated, which means we have this high derivative here. So Fisher information would be large, right? And Fisher information is just j of x. So if n of x is small, j of x would be large. And how does this play out? So this stance inequality gives us that their product should be greater than equal to 1, or basically jx is greater than equal to 1 by nx. So if nx is small, jx would be big, right? And vice versa. So let y be root gamma x plus z, where x and z are standard normal variables, so all are n01 and they're independent, x and z. Suppose we only observe y. Again, based on this observation, we want to reconstruct x, where the function g is chosen to minimize the mean squared error. What is the mean squared error? The best estimator. So we know what the best estimator is, right? So if we observe y and we want to estimate x, the best estimator g of y would be just expected value of x given y, right? Y is something we observe, and yeah, x is something we want to estimate, and we want to minimize the mean square error. So this conditional expectation is the best estimator, and so all that remains is to just compute this best estimator and compute this expected thing. All right. So okay, so let's see what would mean squared error be. So MSE of G, right, of this conditional expectation is expected value of x minus x given y the whole square, and you can write this as expected value of, again, all this conditioning game here, so x minus expected value of y the whole square. Okay, this was already there. Now condition it on y, right? So we condition it on y, and this is that expectation, and then we have this final expectation outside, which is the same as thing above. Okay, so what this means is that we have this. What is this? So if you fix y, if you know y, this thing is the conditional mean, right? And so this thing, this entire inner expectation becomes conditional variance. Conditional variance of x given y. So we basically want to compute conditional variance of x given y. Okay. So what would that be? So let's compute p of x given y. Right. So what is p of x given y? So we'll apply the base rule. So we have p of y given x times p of x by p of y, right? So let's see. So what is p of y given x? So once, if you're given x, y is just this root gamma x plus z, where z is standard normal, right? And you know x. When we say y given x, we assume that we know x. So this would just be, what would this distribution be? This would just be normal distribution with mean root gamma x and variance 1, right? Because y is root gamma x plus z. We're assuming that this is given, so this is a constant and this is n01. So we are just adding a constant to this n01, right? And so this would be y given x. So y given x is a normal distribution, and so we can compute its density. Okay, and similarly, okay, px we already know is n 0 comma 1, right? Right, and what would be py? Py is just, it's the unconditional thing, so it's a sum of two Gaussians, right? where where both Gaussians are zero mean, and so the mean would be 0 for y, and the variances would just add up, right? So the variance would be, this is the variance of z, and then plus gamma. So this is the variance of x, right? Because again y is this root gamma x plus z, and we are not conditioning on anything. We are just, this is unconditional expectation of y. So it's just addition of two independent Gaussians, right? Okay, so you have all these things, and now so which means p of y given x is, okay, so all these were, okay, this this is like lazy equality, whatever these three things. What this means is the density, the distribution is this normal, and so now we write the precise density. This would be 1 by root 2 pi. Okay, so it is this thing here. So we want to write the equation for density of a normal random variable with mean root gamma x and variance 1. So e power minus, right, and the y is the variable here, so y minus, what is the mean? Mean is root gamma x, so root gamma x square by variance is 1. So right, so this is, we are assuming x is fixed here, so root gamma x would be the mean and y is the variable, right? And similarly you can write it for pxx and pyy, and based on that what you will see is that px given y would also be a normal random variable, okay, uh, with some mean, right? And the variance would be like 1 by 1 plus gamma. Okay, so just plug everything here, right? So plug everything here, y given x, then p of x and p of y, and then do that completing the squares thing where you write everything as, so p x given y would be 1 by root 2 pi e power, write this as x minus something the whole square by 2 times something, right? So this thing would become the mean, and this thing would become the variance. Okay, and that would come out to be 1 by 1 plus gamma, right? So A is the correct answer. And for the standard normal, we have also seen that g of x, which is the Fisher information, is also 1. So B is also correct here. Right, and C and D are wrong. Right, so this is just an exercise in computing conditional expectation and conditional variance. Question number 5. Okay, conditional expectations. So hopefully we are comfortable with conditional expectations now. So we want to see which of the following are correct. Okay, so we have expected value of fx given y times gx, and this is just saying that, okay, so this is true if x, y are independent, right? But here we are not given that they are independent, so A is incorrect in general. Oh, and why would it be true? Because then fx given y would just be expectation of fx, right? And so this thing would be expected value of fx times gx. Okay, so this is not true even if they're independent. So, I think so. Okay, what would this be then? This would be expected value of fx times gx given x, right? This would be true. No, right? So this would just turn out to be expectation of fx into expectation of gx if they're independent. So which is not the same as expectation of fx times gx, right? So this is incorrect. This is not true even if they're independent. B is okay. So this is expected value of fy given y. So once you're given y, what is your best estimate of fy? It would just be fy because you're given y, right? So fy would come outside, and so we'll have expected value fy into gx. So B is correct. C is we have expected value of fx given y times g of y. Okay, so now we have expected value of fx given y times g of y. We can also write this as expected value of fx times gy given y. And why can we write this? Because okay, so we have one big expectation outside. Okay, because once you're given y, g of y is just a constant, so g of y can come out, right? So which means so this right so that is why these two are equal. Okay, and so now it's just this expected value of conditional expectation, which is just the expected value. So this would just be a fixed gy. So C is also correct. D is again similar thing. I think, yeah, you just take conditioning with respect to x. So this thing inside is same as expected value of fy gx given x, right? Because once you're given x, gx essentially becomes a constant, and so it can come outside like this, right? And then you have expectation of conditional expectation, which would just be expectation. So D is also correct. Question number 6, let x be a random variable, fg be functions, positive functions, non-negative functions. Let p be 1 to infinity. Which of the following are true? So, right, so it's expected value of fx plus gx p to the whole 1 by p, right? And we know that, so fx equals x to the 1 by p. This is a concave function, right? So if we just apply Jensen's inequality, right? So this is basically this. So we can take this 1 by p inside, but this inequality would be this direction. So it would be expected value of fx plus gx to the p times 1 by p, which is expected value of fx plus gx. Right, so B is correct. C is the opposite direction, so incorrect. And right, and okay, so now since f and g are positive functions, what this means is this is same as mod fx plus gx p to the power 1 by p, right? And this essentially defines a norm. So this is like, I don't know if you're familiar with this, but this is the pth norm of fx plus gx, right? And this norm satisfies triangle inequality, and so this would be plus gx of p, right? And if you want to look it up, I think this is called Minkowski's inequality, right? Which is basically a triangle inequality for these general norms. So for this pth norm, okay. So C is again correct. D is incorrect. Right, so we know that this fxp would just be expected value of fx mod fx to the power p 1 by p, but since f is positive, this mod is same as the normal fx here without the mod, and similarly with gx, right? So this is again triangle inequality Question number 7, let pxy and qxy be joint distributions of random variables x comma y such that py given x is same as qy given x. Which of the following are true? From the answers to this question, can you see why data processing inequality holds for KL divergence? Okay, let's see if we can see this. So let's apply chain rule, right? So we have d pxy and qxy. This is pxqx plus d py given x qy given x, right? And you'll have to do this for every x. I mean, this is a random variable, the second thing, because depends on x, and so you have to take expected value of this, where x comes from p of x, the first thing here. All right. So, and another notation for this second term is d py given x qy given x given px. Right. This is just notation. So right, and so now py given x and qy given x are equal. So this equality is given, and what this means is this is true for every x equals x small x. So for every small x, right, p of y given small x would be a distribution, q of y given small x would be a distribution, and they're same and they're equal for every x. So this term inside is 0, and so for every x, and so expected value will also be 0, right? So A would be correct. So on the one hand we have this, right, because this is 0. Okay, so now on the other hand we can apply chain rule uh, by first taking out pyqy instead of pxqx, right, plus uh, p of x given y, q of x given y, where y is coming from p of y, right? So this is something, and okay, and this can also be seen as KL divergence between this p of y x given y and p of y q x given y, right? So this defines some joint distribution, and this also defines some joint distribution where marginal of y is p of y and conditional is q of x given y. Okay, and you can just see this by writing out the formula for the KL divergence and taking expectation with respect to py. Okay, so this thing is basically a KL divergence. So now, so C is correct. So C is exactly what we've written here, and D is incorrect. D confuses py with qy. So this is right. So D is also wrong, and B is also wrong. Okay, so we have these two formulas for pxy and qxy, KL divergence between pxy qxy, which means that d of px qx is equal to d of py qy plus d of something, right? This, and this we know is greater than or equal to 0 because this is a divergence. Okay, so what this means is d of px qx is greater than or equal to d of py qy, right? And this is basically called the data processing inequality. Okay, it's like you had some input distribution x, suppose you passed it through this channel w, and your output distribution is y. And what is w? W is some conditional distribution, say w of y given x, right? For every x, what is the probability of observing some y, right? That is what a channel is. So px comes here and we get py, and similarly qx, if qx comes here we get qy. And what this says, data processing inequality, that this distance here on the left is greater than this distance on the right. So when you pass it through something, you are basically averaging things out, and that reduces the distance for information theoretic quantities. So um, right, and this channel, what this channel is here is represented by py given x, which is same as qy given x, and that is why we had this thing here, right? That pxy qxy is just same as k dash into px and qx, right? So this is py given x, qy given x, and so yeah, this is basically data processing. And we derive this by expanding this K divergence in two different ways, right? One where we start with the px and qx, and then one with where we start with the py and qy. Okay, let's pxy with a joint distribution of independent random variables. Which of the following are true? Okay, yeah, pq hypercontractive. So what does this mean? Pxy is pq hypercontractive. It means that the the qth norm or the pth norm of wf is less than equal to the qth norm of f, right? And this is true for all f, such that this qth norm is less than infinity. Okay, so this qth norm should exist, uh, right? And what is this w? So what is this wf? So f is a function. F is a function from, right, x to y, suppose, right? And wf, so not x to y, but x to r, suppose. And wf would be a function, wf is a function from y to r. Okay, and how do we define, and what is this function? This would be for a given y, right? This function assigns this value to wf. This would be expected value of f of x given y is equal to y, right? So again, you can think of this as some kind of smoothing which is going on here, that you had some function f of x, suppose, right? And there is some channel or something in between, right? And this channel, this is represented by this conditional distribution and things. So say p, this is p of y given x, and this is p of x. So x is sampled from p of x. Then you have this f of x, right? This is passed through this channel, and and you get something, right? You don't get anything. So wait, you have this x which is passed through the channel, and you get some y. Okay, and uh, now looking at this y, you want to come. Okay, look at y. What is the best estimate of f of x for some given x? Right, and that is this expected value of fx given y. Right, you can see y, but yeah, you cannot see what x is, so you cannot compute f of x. And you just estimate it, and this is the best estimate, and this is some expect. So so once you observe y, you don't know what x is, but you will have a conditional distribution of x, right? So you will take the expected value of f of x with respect to this conditional distribution, right, which is same as this. So now which means you're uh, in a sense smoothing this function out, right? Because you're integrating this function f of x, p of x given y d of x, right? And at for so this is wfy is this. So to compute wf at y, you are just integrating fx over all x, but with respect to this distribution x given y. So you're smoothing your function. Okay, so all this is just to say that you're smoothing things. Okay, when you have this WFF, so WF can be seen as a smooth version of f, and right, and hypercontractivity is so hypercontractivity is so WF is smooth, and so what always happens is the pth norm or the qth norm of WF will always be less than equal to the qth norm of f. But what hypercontractivity says that uh, you have this the pth norm is also where p is more than q or more than equal to q, right? This is hyper. So this is the usual contractivity, and this is hypercontractivity when p is strictly greater than q. So qth norm being less than qth norm is okay, but pth norm is generally bigger. Uh, so we are saying that pth norm of wf is smaller than the qth norm of f, where p is bigger. So this is a stronger statement, and that is why we call this hypercontractivity. There's a hypercontraction going on. Okay. Okay. So yeah, so just to review for myself what hypercontractivity is. So now let's see what do we want to find. Oh, so okay. So x and y are independent random variables. Um, yeah. Okay. So x and y are independent. What would that mean? So WF of y is expected value of fx given y equals y. And since x and y are independent, you don't get any information about x when you see y. So your conditional expectation of x given y is same as is same as so same as the expectation of this original. Yeah, so your conditional distribution p of x given y is same as just the marginal x p of x, because given y you don't get any new information, right? And this is true for all y. So so look what is happening here. It's like this is a constant function. So WF is a constant function, right? So if x and y, and like I was saying, WF is a smooth version of f. So you have smoothened things out so much that the smooth the WF becomes a constant. It's like perfectly smooth, right? And so you've lost all the information about x and everything. So about y, right? So this is perfectly smooth. Um, and so now we know that WF. Okay, we want to do everything in terms of this SP factor. So what is SP? SP is so suppose you are given, right? We have this FQ and then we have this WFP, right? And we want to find the highest P for which this holds, right? What is the for which this holds for all F, right? So highest P would be, I mean, as P grows bigger than Q, the contractivity becomes strong, as we discussed, right? So we want the best possible P, and so this is given by this factor SP. So let's say the best possible P is P star. So that would be Q by SP. Okay, SP is less than 1, so in this Q I think this is greater than equal to Q, right? So this is the high for a given Q. This is the highest P. Okay, you can think of it like this. So um, yeah, okay. So WF is a constant function. So we know that WF of Q is less than FQ. I mean, this is the usual contractivity. This always holds. Now we want to see how much can we increase this left hand side Q. Can we increase it more? Okay. So since WF is a constant function, this is same as WF infinity. Okay, so what are these norms? Suppose we have this y here. What is this pth norm of y? This is just the expected value of x power p 1 by p, right? And suppose x is a constant, say if let's say this is x. Okay, we want the pth norm of x, and so this is by definition this. And suppose x is a constant. Suppose x is constant, right? So x is equal to 5. So then this becomes what? Then there is no use of this expectation, right? So because 5 power p times 1 by p, this is 5. So xp is 5 for all p. Okay. If x is equal to 5, this random variable is a constant random variable. Okay. And so what this means is that wf of q would be same as wf of q plus 1. Okay, this would be same as wf of q plus 2, and so on. You can increase it how much ever you want, because wf is a constant. And why is this a constant? Because independence, right? And so this p can be made infinitely large. So what would that imply is that this sp is 0, right? So for a given q, you can take largest p to be p star to be qi0, which is basically infinity. So yeah, this is all informal maths, but yeah. Okay, so you can take p star p as big as you want, right? So A is the correct answer, and C is also correct because 0 is less than equal to 1. At question number 9, let Pxy be the joint distribution of random variables x comma y. Okay. So x is 1 with probability half and x is minus 1 with probability half. Okay, and given x, y is equal to x with probability 1 plus rho by 2, and y is minus x with probability 1 minus rho by 2. Okay, so where rho minus 1 to 1 is a constant, let f be some function from minus 1 comma 1 to r, where fx is defined as this. Which of the following are true? Okay, so we want to compute this wf of y for this function, for this linear function. Okay. Yeah, so wf of y is this expected value of fx given y equals y. And what is fx? It's a plus bx given y equals y, which is same as a plus b expected value of x given y equal y. Okay, so we basically want to compute expected value of x given y equal to y. Okay, we are given y given x, right? We are given x, so we can compute p of x given y. Okay, and since x and y both are just variables over one random variable, so sorry, over this 2 point minus 1 comma 1. Okay, so we have to compute p x equal to 1 given y equals y, and p x is equal to minus 1 given y equals y. Okay, and then you can compute this expectation, right? And so if you just do the computations, what you will see is that expected value of x given y is equal to rho if y equals 1 and minus rho, right? Let's say y equals small y. So if small y equals to minus 1. Okay, and this can be written as rho of y, right? Because if y is 1, this just becomes rho, and when y is minus 1, this becomes minus rho, which is same as this above, right? So yeah, so basically we have a plus b rho y, okay, which is option number C. Okay, so we have this, the final question. Consider the same setting as in question 9 above. It is a known fact that any arbitrary f can be expressed as, okay, so any arbitrary f from this 2-point set, right, this two cardinality set, any f can be expressed as this linear function. Okay, so I mean, this is easy to see. Suppose f of my, how will you define a function, an arbitrary function? Suppose f of -1 is alpha, f of 1 is beta, right? And we are saying that you can express this as a linear function. So L, so let's say that linear function is L. We are saying that you can express it as Lx a plus bx, where a and b are some constants. So if, right, so if x is -1, L of -1 would be a minus b. If L is 1, sorry, if x is 1, then L of 1 would be a plus b, right? And now you can solve these two equations to get something for a equals something and b equals something, right, in terms of alpha and beta. So, and then you can just plug it in this L of x here. So, okay, so what I'm saying is about, I'm trying to justify this fact that any arbitrary f can be expressed as this for some constants a comma b, right? Which of the following are true? Use the definition of PQ hypercontractivity and explicitly compute the expectations. Okay, so all these options deal with 2,4 hypercontractivity. Okay, so we want to say for which row is pxy, right? So what is pxy? Pxy is same as px, p of y given x, and we saw that p of x is like plus minus 1 each with probability half and half, right? And p of y given x is y is equal to x with probability 1 plus rho by 2 y given x, and it's minus x with probability 1 minus rho by 2, okay, the same as above. So this defines the joint distribution pxy, and we want to comment on the hypercontractivity, 2,4 hypercontractivity of this distribution. Okay, so what we want to prove is, we want to, okay, what is 2,4 hypercontractivity? Take any function f, wf, okay, so wf of 2 is less than or equal to f of 2. This is the usual contractivity. This would always happen. We are interested in this happening, okay, that wf of the fourth norm of wf is less than or equal to second norm, okay. And so our question is, for what values of rho this happens for all f, okay, this is one, right? And now this fact says that you only need to worry about linear f's, okay, since you have this f, you're interested in all functions from this minus 1 comma 1 to r, and all these functions can be expressed as f is equal to a plus bx for some ab in r. All right, so let's only need to worry about linear functions. So we'll compute this. So we want to see for what values of rho does this inequality hold for all linear f's, okay. So let's see, what we know, that wf of y is a plus, what was it, a plus b rho y, okay, a plus b times rho times y. And so what is wf4? What is this fourth norm? This is same as expected value of a plus b rho y to the power 4, the whole raised to 1 by 4. Okay, and similarly f of x is a plus bx, and so the second norm would be expected value of, and we know that f of x is a plus bx. Okay, so we want, okay, we want this to be less than or equal to this, right? We want for which rows, row r rho, for which rows this is less than or equal to this. Okay, now it's just, yeah, take, we want to remove those 1 by 4 and 1 by 2. So uh, take to the power 4 on both sides. So our question becomes, for what row, for what rows, uh, okay, and we can remove the mod as well because these powers here are even powers 4 and 2. Okay, so it just becomes a plus b rho y to the power 4 is less than equal to the value of a plus bx the whole square, the whole square. Okay, uh, for which value of rho does this happen? So now just expand this. So what you get is a power 4 plus, you will have, okay, plus 4c1. Okay, this is that binomial thing. A cube b rho y plus 4c2 a square b rho y the whole square plus 4c3 a cube a b rho y the whole cube plus 4c4, which is 1, b rho y to the power 4. Okay, and then you have this expectation outside. So this expected value of y would be 0. Okay, if you just compute the marginal of y here, you'll see that marginal of y is also plus 1 and minus 1 with probability half and half. And this 1 plus rho by 2, 1 minus rho by 2 was y given x. And we know what x is. So if you compute what the marginal of y is, you'll get this. Okay, so marginal of y, so expected value of y is 0. Similarly, expected value of y cube would also be 0. So these factors go to 0, right? And similarly on the right hand side, okay, and moreover, what would be y square? Y square would just be 1, right? Similarly, y4 would just be 1 because y is either 1 or minus 1. Okay, and similarly, the right hand side would be a square plus b square into expected value of x square, which is again 1, plus 2abx, and expected value of x would be 0. So this becomes a square plus b square to the power whole square, right? This is this square here. Okay. So our question becomes, for what rows a power 4 plus 4c2 is 6, 6a square b square rho square plus uh, yeah, b4 rho 4 is less than equal to a square plus b square the whole square. Okay, and so let's see, suppose we take rho equals 1, what happens then? Does this, and this, for what rows? This holds for all AB because we are interested in all functions, right? So this should hold for all AB if you want to say that thing is hypercontractive for a given row. Okay, so for row equals 1, what is LHS? It's A4 plus B4 plus 6A square B square, which is A square plus B square the whole square plus 4A square B square, which is not less than equal to, right? So which is not less than equal to A square plus B square whole square. I mean, this is equal to when either a square or b square is 0, but we want it to hold for all a square b square. So this is not true, right? So for rho equals 1, your pxy is not 2 for hypercontractive. So b is incorrect, right? Let's see what happens for rho equals 0. For rho equals 0, the left hand side becomes a4, and right hand side is a4 plus b4 plus 2a square b square. So left hand side is less than equal to right hand side for all ABs, right? And so it is hypercontractive when rho equals 0. Right? And rho equals 0 is basically, I think, yeah, so x and y become independent, and right, and we saw that 2 4 I mean you can have 2 infinity hypercontractivity for independence. So yeah, so C is correct, that this is 2 for hypercontractivity for rho equals 0, right? D is incorrect because we saw that for rho equals 1, this is not hypercontractive. And similarly, if you just plug in rho equals 1 by 4, right? You just plug in rho equals 1 by 4 here, you will see that this inequality holds for all a comma. Right? And so A would also be correct. Okay. So I hope this discussion makes somewhat clear what hypercontractivity is. And this question was to make you explicitly compute, like, I mean, what is 2 for hypercontractivity, right? So for some values of rho, this pxy is not 2 for hypercontractive, and for some values of rho, it is 2 for hypercontractive. Right, and we saw that by explicitly calculating all the expectation of WF and F. And here things were simpler because we want to claim something for all F, and for these kind of domain where F is from -1, 1 to R, we know that any F can be written as this linear function. And so finally what we had to verify was just this condition here in red box, that this condition, if it is satisfied for some rho, right, for all a comma b. So fix a row, and then this condition is that should be satisfied for all a comma b. Then we say that this is 2 for hypercontracting for that row. Okay. Okay, so that ends all this question for week 7. Um, so I think this is the last live session because next weekend is the exam for this course, and the deadline for assignment 8 hasn't passed yet, so I cannot discuss that. But I saw the questions for assignment 8 and they're not related to concentration inequalities much. Those are like questions from linear algebra and probability, and those questions are, I mean, those results are used to derive concentration results in and week 8 lectures. Okay, so yeah, so okay, so what I'm trying to justify here is that even if I don't discuss that week 8 assignment, it's okay. Those are like standard linear algebra and probability results. Okay, and I hope you enjoyed the course. So okay, bye. Adieu.